Question 42. Between which two lithospheric plates could this boundary be located? Well, they show you a boundary over here, and they show you that this is a continental crust, and this is oceanic lithosphere. So, and this arrow that they show you over here means that the oceanic plate is going downwards, and the continental crust, the continental plate, is staying intact. So look at the earth science reference tables that you get, look at the tectonic plates, and if you look, you'll see, when you look through the whole thing, it's not that big. You see South America is on one side. If you look in the middle bottom of the map, you'll see South America is on one side. You have the South American plate, and the left side you have the Nazcan plate. So you have two arrows, and then you have this funny looking thing. You have a line with these blacks sticking outwards towards South America. So if you look at the key, that means that there's a key that shows you what everything means. So these things that go like this, this line and then these big things means that this side, the side to the right of these boxes, is that's going in top. That plate is staying in top. And these two arrows means that these two plates are coming towards each other. So one goes on top, and if one goes on top, the other one goes on bottom. And that's similar to what you see in this diagram. You see the continental crust is on top, and the oceanic lithosphere is going downwards. They show you an arrow that shows that it's going downwards. So the only place where that is you have the Nazca plate, and you have this line, and you have these things sticking outwards towards South America, which means that the Nazcan plate is going downwards when the South American plate is going towards it, must be going on top. So the correct answer to question 42, between which two lithospheric plates could this boundary be located, is answer 3, Nazca plate and South American plate. Question 43. Compared to the continental crust, the oceanic crust is more dense and thinner. Question 44. The temperature of the asthenosphere at the depth where melting first occurs is inferred to be approximately how much degrees Celsius? We give you 4 choices, between 100 degrees Celsius and 5,000 degrees Celsius. Well, you're going to have to look at the inferred properties of Earth's interior on your reference charts that you get on the regions. So in the inferred properties of Earth's interior, you see we're looking for the asthenosphere, because you see by the asthenosphere, you see it shows that's where the melting occurs, down here, near somewhere in the asthenosphere. So you see a asthenosphere, so you map backwards. Here's the asthenosphere in the map. You go backwards this way, it's on the top of the map. Here's the asthenosphere, lower is the stiffer mantle, more lower inwards is the outer core, and all the way in is the inner core. You see the inner core, if you trace all the way to the left of this diagram, that's called the inferred properties of Earth's interior, it's 6,000 degrees Celsius. You go up to the outer core, it's between 5,000 and 3,000 degrees Celsius. Then you go up to the stiffer mantle, it's between 3,000 and 1,000 degrees Celsius. Finally, the asthenosphere plastic mantle is between 1,000 and 0 degrees Celsius. That's just across this line. However, if you go more inwards, you'll see on top also it goes from 0 to 6,000 degrees. And when you go up this way, you'll see that there's a dotted line between 1,000 degrees Celsius and 2,000 degrees Celsius, going all the way downwards from there till about 3,000 degrees Celsius at the end of the temperature map on the inferred properties of Earth's interior. So the melting point, remember the asthenosphere is on top, right? There's the inner core. The inner core is the most inner one. Then there's the outer core, the stiffer mantle, and then there's the asthenosphere. So take this atmosphere, and you want to see the melting point in this atmosphere. So you see it's between 1000 and 2000 degrees Celsius. So now, it's approximately what? 100 degrees Celsius, is that between 1000 and 2000? No. Answer 2, 1300 degrees Celsius is between 1 and 2000. 4200 degrees Celsius is not between 1000 and 2000. And 5000 degrees Celsius is not between 1000 and 2000. So the only answer that could be correct is answer 2. Because you saw in that map that the melting point, that dotted line shows the melting point, that it starts where the heat is above 1000, between about 1000 and 2000 degrees Celsius, and then going upwards as it gets hotter it melts quicker, but that's where it starts melting, between 1000 and 2000. So it's approximately, we'll say, 1300 degrees Celsius. So the correct answer to question 44 is answer 2, 1300 degrees Celsius. Question 45. Point X, that's over here, this point, is located in which earth layer? Well, you're going to have to look again at the inferred properties of Earth's interior, that diagram. And find point X. We know that point X is in a lithosphere. So the question is, where is the lithosphere? So you'll see that the lithosphere is these two things, right? And that's the crust and the rigid mantle. So underneath the crust is the rigid mantle, that's where X is. The lithosphere represents these two things, and you see right under the crust you see the rigid mantle, and that's part of the lithosphere. So where is X located? Answer 1, in the rigid mantle, which is answer 1. Question 46. Base your answers to questions 46 and 47 on the diagram below. Diagram 1, that's the circle, represents a cross-section of Earth and its interior layers. That means you slice the Earth in half, and here's the inner core, here's the outer core, which is a liquid, and then there's the mantle, and then there's the crust. Then you have this point over here, which is the epicenter, where the earthquake occurred. And in diagram 2, they tell you that they had, there were 4 seismograms where it was recorded the strength of the earthquake at 4 different stations A, B, C, and D. And the diagram, so that's what you have over here. In station A, you see the S wave and P wave arrivals were very, very close. So what is it called? And then as it goes on, the S wave arrives later. That means what arrived first? The P wave arrives first. Why does the P wave always arrive first? Because it's much faster. The S waves take longer to reach those stations A, B, C, and D. Now, question 46. Which list correctly matches the seismograms with the seismic stations where they are located? Well, let's see. Point A is the closest to where the earthquake occurred. So therefore, if let's say you have, pretend like the P waves and the S waves is one person's walking and the other guy, one person is riding a bike, the other guy is driving, or one person is driving, the other person is flying a plane. So the P waves are going much, much faster. So they'll hit the point much quicker. So over here, the P and S waves are very close. That means the S waves came not that far after the P waves. And as you go on, you see the S waves are further away. Means the P wave arrives way before the S waves. As you see over here, the P wave arrived not that much before the S wave. Over here arrived more before the S wave. And as you go on, the P wave arises much, much before the S wave. And finally at the end, the S wave doesn't even arrive at all. So, so the question is, so A is the closest. So that's 1. What's the second to closest? If you see, D is closer than B because B is halfway down and D is just a little bit down, but it's further than the A. So the P wave and S wave are a little further than in one. One is SN, the S and P are very, very close because the P wave, even though it's going faster than the S wave, it doesn't have that much time to get that much farther away from the S wave. So this is point A, this is point D, because D is closer, but it's further than A, so the S and P waves are further from each other. And 3 is B, because B is halfway down, and you see the P wave arrives way before the S wave. And then number 4, diagram 4, all you can see is the P wave. You don't even see any S wave. How come there's no S wave over here? How come they didn't make it longer and make an S wave? Well, since the epicenter was over here and you had to go straight down, so the shock of the waves from the earthquake would have had to go straight through the earth, and would have gone through the outer core, which is liquid. It would have been absorbed because S waves cannot go through liquid. It has to go through solids. So therefore, it's 1 is A because the S and P are close. The second diagram is D because it's a little further than A from the epicenter. So the P waves come a little bit earlier than the S waves. Let's say over here it's let's say a time. We'll call this a distance of 1 time. And over here it's a distance of 2 times. Over here it's a distance of 5 times. So in 3. So A is closest. D is a little further. So the S wave comes much later than the P wave. B is even further. So the S wave comes much, much further than the P wave. And C, there's no S wave because it's all the way down. So the correct answer, the answer 46, is 4. That 1 is A, 2 is D, 3 is B, and 4 is C. Question 47. Station D is 8,000 kilometers from the earthquake epicenter. Question 47. Station D is 8,000 kilometers from the earthquake epicenter. How long did it take for the P wave to travel from the epicenter to station D? So it asks how long did it take the P wave to reach station D, and it says the station D is 8,000 kilometers. So they're asking how long did it take the P wave to travel 8,000 kilometers. So you look at the graph you're given on the regents on earthquake, P wave, and S wave travel time. If I would have written the whole thing out, it would have been not that clear. So I just wrote time, minutes, travel. I wrote from 0 to 12 minutes. And distance of traveled, for the P and S waves, I did from 0 to 1, 2, 3, 4, 5, 6, 7, and 8,000 kilometers. So this graph that I made on the board is only part of the graph you get on the regents, but this is all we need because we want to know how long did it take to travel 8,000 kilometers from the origin, from where the earthquake happened at 0. So the further the distance, the more time it takes to travel. You see the S wave over more time travels less. The P wave travels more than the S wave does over time, because you see the P wave from 0 kilometers to 8,000 kilometers, it took, this is minutes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 8,000 kilometers this is broken up into, it breaks the minute into 3 parts, right? This is 0, 20, 40, 60. That means the next hour is 0, so it's 20, 40. So this is 11 minutes. And 8,000 kilometers, it's 20 seconds. 11 minutes and 20 seconds. So that's answer 2. The correct answer to question 47 is answer 2. So that was the P wave. So you see the P wave in 8,000 kilometers traveled up in 11 minutes and 20 seconds. It traveled 8,000 kilometers. Now let's see what the S wave did in 12 minutes. This is longer than 11 minutes and 20 seconds. In 12 minutes, the S wave only traveled less than 4,000 kilometers. So you see the P wave moves faster than the S wave. That's something from last question. So the correct answer over here, the question 47 is answer 2. That station D, which is 8,000 kilometers, it took the P wave from the epicenter to station D, which is 8,000 kilometers. 8,000 kilometers on the earthquake P and S wave travel time graph. You go 8,000 kilometers, right? Epicenter distance, which is times 10 to the third power kilometers. 10 to the third power is 10 times 10 times 10, which is 1,000. So this is 0 times 1,000, 1 times 1,000, which is 1,000 kilometers. 1, 2, 3, 4, 5, 6, 7, and this is 8. At 8,000 kilometers, it took the P wave 11 minutes and 20 seconds to reach station D, which was 8,000 kilometers away. So the correct answer to question 47 is answer 2.